So for this one, let's say we have a sphere, just to change for non-uniform charge density. So, a sphere. Consider a sphere of radius capital R again. But now the charge density rho is equal to some constant. Let's say the constant is B. I'm avoiding the letter A because it refers to area. It's some constant B times, let's say R. Some constant times R. That's the charge density. So it's non-uniform, right? Meaning when R increases, the density increases also. Charge density increases with R. And so the question, what's the electric field inside and outside of this sphere? To find the electric field inside and outside. So let's start with inside. Right? Inside the sphere. We know what should we do to find the electric field? Apply Gauss's law. Charge distribution, even though it's non-uniform, it's still spherically symmetric. It still has spherical symmetry, meaning the charge density here is the same if I go around the circle or around the whole shell, because as long as you keep R constant, rho is going to remain constant. So the electric field will still be radially outward. If it's radially outward, then it's parallel to the area. Draw my Gaussian surface, I think we all agree it should be a sphere, right? Of radius little r should be less than capital R. So E dot dA becomes EA, which is, what is the area here? What's the area?
4 pi.
4 pi. 4 pi little r or capital R? Little r, it's the Gaussian surface. It was 1 over epsilon naught. Now, earlier, when we had uniformly charged sphere, we said the charge enclosed is rho times the volume. But rho is not uniform. So this has to become an integral. It becomes this. Rho dB, where dB is the volume. That's the difference. And our integral will go from 0 to little r. So we get 1 over epsilon naught. Integral from 0 to little r. Rho is b times r. And then dB. So, what is dB for a sphere? Or volume? That would be for an entire sphere. But here, I'm looking for just dB. Remember what we did, right? So we can break it into spherical shells. Each shell is radius r and thickness dr. What's the volume of just that one little shell?
4 pi squared dr.
4 pi r squared dr? Or 4 pi r dr?
4 pi.
You change your mind.
I got 4 pi squared dr.
4 pi r squared dr, yes. It needs to be, it has to be length cubed, because it's a volume, right? So it has to have the same, so yes, so it is this, 4 pi r squared dr. Remember the intuition behind this. I said, if you have a ball, okay, one of those plastic or rubber balls, And what's the surface area? What's the volume of just the ball, of the skin of the ball? Well, if you want to find the volume, just cut it with scissors and flatten it. When you flatten it, the area is 4 pi r squared, and the thickness of the ball is dr. So that's the volume. So that's what we do. Then that is the 4 pi. So here you have E times r squared. On the right side, you get d over epsilon naught. And then you have r times r squared is r cubed, right? When you integrate r cubed, you get r to the 4th over 4. So you get just r to the 4th over 4. And then divide both sides by r squared. So that's the electric field inside. Outside it will be like a point charge. When you exit, correct? Once you're outside, it's like a point charge. Would you like to go to do it for the outside, or just stop and continue for the outside? Outside, where would the Gaussian surface now be? And the radius is r, right? Center of so this is r greater. We got E dot dA. What does the left side become? E dot dA. Which is 4 pi r squared, right? Which is the area, surface area of the Gaussian sphere. E times 4 pi r squared. Right side, you get 1 over epsilon naught, Q enclosed. Remember, Q enclosed, you can't just say rho times the volume because it's non-uniform, so it would be rho BD. And so you get 1 over epsilon naught. E times r. Now, what are the limits of integration now? So, big R, so it's good.
No, it's from 0 to.
From 0 to big R, right? Yeah, because here there's nothing. 0, 4 pi. Here we have E times r squared. D over epsilon. R cubed, when you integrate, you get r to the 4th. Right? When you substitute from 0 to r also. Then you get right after 2. Are we surprised that we got 1 over r squared or not? No, because it's like a point charge, right? We exit. Sounds good. There's a conceptual question that I thought was interesting in one of the exams. I think problem 3, fall 2023. Here is an infinite line. Infinite line. Charge density is lambda. So good. It's an infinite line. Suppose we put a cube. A cubical box around it. Suppose we put a cubical box. Sounds good. Suppose we have a cubical box around this infinite line of charge density line. The question is, what's the flux? Find the flux through this box. Find flux. Any ideas?
Take it from like each side, or
Yeah, sure. There will be flux to each side, probably. The problem is that's going to be tough to calculate through direct integration because we know the electric field is in the radial direction, right? Because it's an infinite line. It's lambda over 2 pi epsilon naught over r. The reason is, suppose the box, by the way, I forgot to tell you, the box is length L. It's cubed, the L by L by L. It's L on each side. Yeah.
The box centered a lot.
Sure.
So where does it go?
Not quite, no. What does Gauss's law say? Flux is equal to what? Yeah, E dot the air, enclosed interval, or you can say flux. Instead. This is hard. This is easy. What's the charge enclosed within our box?
Lambda L.
Lambda L. Can I erase here?